So while your colleagues are streaming in physically in the room, welcome to today's session of the course. What we're going to do today is to work more with deterministic finite automata, and we will also introduce a variation on finite automata, which go under the name of non-deterministic finite automata. So as usual, before starting with the new material, let's warm up. Let's get our neurons buzzing by solving a puzzle that Dr. X has posed me. Now, Dr. X likes comics, and one of his favorite comic characters is a guy by the name Corto Maltese, or if you want to sound English, even though you shouldn't, Corto Maltese. Actually, that's an Italian character, so it should be Corto Maltese, anyway, for what it's worth. Fantastic comics. If you're into comics, you should read that. Especially this one, The Ballad of the Salt Sea. Umberto Eco, whom some of you might know because as the writer of The Name of the Rose, famous semiologist, philosopher, and writer, he says that when he wants to relax, he reads Plato. When he wants to think, he reads Hugo Pratt, who's the writer of these comics. Of course, he's pulling our legs, but anyway, that's a good quote. So Corto Maltese, just to sound a little bit English, wants to save the inhabitants of an island in the South Pacific. He's a traveler, he's a sailor, he's a very cool guy. But to do so, he needs to build a DFA, and he doesn't know how to do it. But we do, don't we? And this DFA should accept all of the strings of A's and B's that do not contain the patterns AA and AAA. Can we help him? Of course we can. So let's do it. I'm not giving you any time limit, but we should do it within today. Okay, so that's what we need to do. All strings of A's and B's without A's, AA, and without AAA. So I'll draw the start state of the DFA. Well, you know, sometimes, in fact, always, before you actually start solving an assignment or you start saving an island in the South Pacific, it's a good idea to pause for a second and think about what you're being asked to do. Now, the description of the problem from Dr. X says, you have to accept, you have to build a DFA that accepts all strings of A's and B's without the pattern AA and without the pattern AAA. Can we simplify this a little bit? Your colleague is saying down there, well, it's enough that we check that the pattern AA is not there. Why? Because if AA is not there, then certainly AAA cannot be there. Because if you see AAA, 3 A's in a row, you also have seen 2 A's in a row. So if you don't have AA, you certainly cannot have 3 A's in a row. The first requirement is stronger than the second. So he was trying to pull our leg and sort of make us perhaps confuse us, but fortunately we are not too confused. Okay, so really what we need to do is to accept all the strings that do not have 2 A's in a row. Fantastic. So let's do it. I'm in the start state, and what I can see is some A or some B. Okay, first question. Should we accept the empty string? Yes, of course, everybody here is saying. Why? Because the empty string does not contain AA. So it's a good string. Let me double circle this thing. Okay, so what if a B comes along? Shall we stay where we are, or shall we go to a new state? We stay where we are, because so long as we see B's, we haven't seen any A's, so we haven't seen any A's. That's what the start state really means. So let's loop. Well, what else can come along? There is an A. Now, shall we stay in the same state or shall we go somewhere else? We should go somewhere else, everybody here is saying. Why? Well, because this could be the beginning of the pattern AA. Okay, what about this state that we go to? Should it be an accept state or not? It should be an accept state. Why? That's right. Why? Because so far so good. We haven't seen anything wrong. Okay, we haven't seen two A's in a row. Okay, what can happen in this state? There could be another A that comes along, or there could be a B that comes along. Okay, so if an A comes along, what happens? Yeah, we should go to another state. And what kind of state is this? Should it be an accept state or not? It shouldn't be, because now we've seen the bad pattern, the one that we didn't want to see. So we wear our garlic necklaces, we go to this bad state, and what happens in this bad state? It's an error, so if we keep reading stuff, we just loop in the error state. Because according to the language specifications, once we've seen the bad stuff, namely two A's in a row, well, we cannot become good again, can we? We need to say what happens if we are in this state here, this one, and we see a B. Where do we go? We go back to the first state, back to the initial condition. Why? Because we've seen an A, it's followed by a B, so we restart our search for the bad pattern AA. Bingo! We saved an island in the South Pacific. That's where we would all like to be right now, to enjoy the sunshine. We can't, but at least we did a good deed for mankind. At least mankind in the South Pacific and in this classroom, and also for you at home, because you've also sort of practiced DFA programming. Before we move on, you know what am I about to ask? Are there any doubts about this DFA, about this solution? So let's clarify the meaning of the states. What does this state means? This state really means the last symbol I read was different from A. It was either nothing or it was a B. This state means last read A. Only one. This means so AA, which is the stuff you didn't really want to see. So if you keep this intuitive explanation in mind, then I think the transitions make complete sense. Why? Because if you're in your initial state, you last didn't see an A. Okay, so if you see a B, then you last didn't see an A. That's why you don't change state. If you instead in that state see an A, well, you last saw an A, so you better go to a state where you remember that you last saw an A. And that's the state in the middle, this one. If in that state you see a B, you go back to a state that allows you to remember that you last didn't see an A, which was the first one. But if in that state you see another A, bad shit happens. You saw the stuff you didn't want to see and you reject everything. Because the string that you just read was not a good one. where our definition of good is, for this specific example, no AA. So far, so good? Warmed up? I am. So let's see what finite automata, in particular DFAs, can do for us. You might recall that at the end of our previous lecture, we were starting to look at the Grape problem. Grape is a command line command, actually, that you can use in Unix to find for patterns, for the occurrence of patterns in your input files. Now, how does that thing work? And how can we generalize, so how can we express as an algorithmic problem, the problem that actually the grep function solves? Well, we have an input that consists of two items of information. We have a text T, which could be your file, which has a given length, small t. And we have a pattern, which is represented by a string W of length n. Now, typically, T will be very long. The pattern you're looking for will be much smaller than the humongous file that you want to search for the pattern W. The problem that you want to solve, at least as a decision problem, is does the pattern W appear in the text capital T? Now, there is an obvious algorithm for doing that. Now, what is the obvious algorithm? You start scanning through your text T, and you search for occurrences of W. If you find it anywhere, you say yes. Otherwise, you say no. And actually, grep tells you what lines, on what lines you actually found that pattern, because it could occur several times. Now, what does scanning mean? Scanning means I start looking at the first symbol in my piece of text, and then starting from there, I examine, in the worst case, the n following symbols to figure out whether they make W. If that doesn't work, well, you start from A2 to see whether from A2 you find W. And then you start from A3, and then you start from A4. The last position at which it makes sense to start looking for the pattern W is the position T minus n, because W is of length n. If you haven't found it by that point, you're not going to find it later, because anything that starts later than that position is too short to be W. Now, how much does it cost? I mean, you're computer scientists. Computer scientists are always concerned with the efficiency of these algorithms. Well, roughly, we do n times t comparisons between characters. The official thing is n times t minus n squared, but n squared is actually much smaller than n times t, because n is much, much smaller than t. So roughly, that's why I say roughly, you do n times t comparisons. Now, since t is really, really long, that's too much. You want to be more efficient if you can. The question is, can we do better? And of course, you know, this is a rhetorical question, otherwise I would not ask it. The answer is yes. And who are you going to call? DFAs. That's who you're going to call. So what you do is you build a DFA that accepts any string with W as a consecutive substring. Okay, so instead of accepting all strings that do not have AA, like in the example that we just solved, we accept, say, all strings that have AA or ABA or whatever string W we are looking for. And then we just feed the file, the text file T, to the DFA M. And if the DFA accepts the text file, the string that corresponds to the text file, then you say yes. Now, why is it better? Well, first of all, it only does T comparisons, because you run through the text file capital T, which is of length T, through the DFA, and you read it one symbol at a time, and that takes T. reads to do. However, you have to build the DFA-M, and that costs. But fortunately, three very smart guys, Donald Knuth, whom you see over here, a guy I've already quoted as saying, everything you can, science is what we can teach to a computer, everything else we do is art. Morris, whose photo I could not find on the net, and Von Pratt, another really smart guy who at some point was a PhD student of Donald Knuth. He finished his PhD in 20 months, amongst other things. They actually developed a very, very efficient algorithm for building the DFA, which is way too advanced for this course, but it exists, it's efficient. And in fact, it's used. It's used by Grape, for instance, among many other algorithms. So you see, in your daily life, you're actually using DFAs without realizing it. At least every time you do a text search using Grape, and in fact, every time you look for some pattern in some file or anything else, there are DFAs inside. Okay, the question is, do the search engines on the net use DFAs? Well, the answer is not really, not really. The reason is that sort of the queries that you pose to Google, to the Google search engine, they have substantially less structure than the query that you pose your text editor when you look for something. The query that you pose your text editor are usually regular, well, they're always regular expressions. Whereas when you ask Google, you don't ask for a regular expression. You ask, tell me all the places where they want to shrink my mortgage. That's much more complicated. So the technology is different. But you will learn about, in these guys, the technology that Google uses to do Google Translate, to do search engines, in the second part of the course. There is linear algebra inside there of some form. Okay, so is grep the only thing where I can find finite automata? Well, the answer is absolutely no. Lexical analyzers in compilers whose job is to take your program and divide it into what they're called tokens are DFAs. Spell checking is done by DFAs. Speech recognition is done by weighted automata, which are DFAs with some weights annotating the transitions, not just the input symbols. Network protocols that you use and love, they can be represented by DFAs. The vending machines that you interact with, perhaps when you're hungry, out there in the sun or wherever else, are DFAs. They don't look like them, but they are DFAs. Most appliances, electric appliances that you interact with, which have software inside, they are DFAs. Your washing machine is a DFA. The elevator here is a DFA. Train switches, well, not here in Iceland because there are no trains, but in most places, train switches are DFAs. Now, the great thing, and I think this shows why you should be curious just about anything that happens around you, because you never know, it could be useful for you at some point in your future life. DFAs are actually being proposed, are an abstraction of something that was proposed by two neuroscientists, McCulloch and Pitts, in 1943. They were proposing a model for the activity of our brains, our neurons, of how they work and how they connect to one another. And they proposed a model which was essentially the model of deterministic finite automata in disguise. This was, of course, too simple. Well, at least we hope. It's too simple to describe what happens in our brains, but on the other hand, it turned out to be just right to do all these things and many more. And there is a hyperlink here, if you're interested, in the original paper, A Logical Calculus of the Ideas Immanent in Nervous Activity by McCulloch and Pitts, that you can browse through at your leisure if you're really interested. So there is an hyperlink on the slides. So there you are. There are Trojan horses on the slides. Okay, so I hope that I've sold you DFAs a little bit more, even more than I did before. Now let's see what more we can do with DFAs. What is the power of these things? Because now we know that they are really cool. And once you have a really cool gadget in your hands, you want to figure out what is it that you can do with it. And at the same time, it's good to know what is it that you can't do with it, so that you don't try to build DFAs for things that DFAs cannot do. You could spend your whole life trying to do that, and you would never succeed, which is a kind of frustrating experience. Then you would end up being like me, the most frustrated human being on earth, or thereabouts anyway. So there is one thing that DFAs can certainly do. No matter what finite language you can come up with, you can build a DFA that accepts it. Now, what is a finite language? A language is what? There is a bit of silence here. I'm sure that at home you're all screaming that the answer is a language is a set of strings. It's nothing more, nothing less than that. It's not a complicated thing. It's a set of strings. A finite language is a set that only contains finitely many strings. So for instance, by way of example, it could be this set that you see on the slide that contains only 4 strings. Now these 4 strings are over the alphabet A, B, C, D. These are the 3 letters that occur in these strings. Can you come up with a DFA that accepts this language? Of course, at home you're saying, yes, we can. And the people here in the lecture room are also saying, yes, we can. So let's do it. Actually, they are not saying, yes, we can, but I make them say, yes, we can. Because they can, I know. So let me copy here the language so that we have it for visual memory. I have AC, and the 4th string was BB, Brigitte Bardot. Okay, so ladies and gentlemen, lo and behold, you at home stop the recording, do it. We in the lecture room are also doing this. Come up with a DFA that only accepts these 4 strings. Okay, so let's start. Actually, let me tell you straight away, we are not going to draw the whole DFA because it could be a little bit messy. We are only drawing part of it, and then I let you fill it in so that you can be messy at home. Okay, so what is it that you can see to begin with? You can see A, B, C, or D. Okay, so let's look at input A. If we see input A, where do we go? To another state. I think that's a good choice. And what should the nature be of this state? It should be accepting. Why? Because the first string in this language says, thou shalt accept A. So if that state were not accepting, we would be in trouble already. And we don't want to be in trouble straight away, do we? Excellent. Now, what else should we consider as a meaningful, as a good first symbol to see? A B. And where do we go with a B? To another state. We need to go somewhere else, because we want to remember that we have seen a B. Now, should this state be an accept state or not? No, because we don't want to accept B, because B is not a string in this language. Okay, so what if I see anything else to begin with, namely a C or a D? Where do I go? Okay, some of your colleagues are saying loop. But is that a good idea? No. Why? Because if I were looping there, I could see, for instance, CD, 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 A, accept. Not good. Since no string in this language starts with a C or a D, if we start by reading a C or a D, we are stuffed. Or, well, no, we are not really stuffed. We just want to be unhappy. So if we see something else, namely a C or a D to begin with, we go into our filupokey mood. Okay? Fantastic. Now, if I am in this state here, what is the only thing I want to see? I want to see a C. And where do I go? To another state, because I want to remember I've seen A followed by C, and now I accept. And from this state, if I see anything at all, where do I go? To the frowny face. Okay, anything. A, B, C, D. Filupokey. Okay, excellent. That's why I'm saying from now on, we only draw the interesting stuff, because a lot of the stuff is going to go to the bad guy. And we are in the bad guy, no matter what I see, I stay bad. Okay, so if I am in this state, what is it that I want to see? I've seen a B. I can see another B and be happy. Or you can see a C and continue. And after I've seen a C, I want to see a D and be happy. And now you have to fill in this DFA with a lot of other transitions that tell you all the places where you can be unhappy. Okay, wouldn't it be nice if we could just focus on drawing the happy stuff? That is to say, this part here. The stuff that we care about, and forget about all the other things. Well, if we are using DFAs, deterministic finite automata, we can't. We are forced to add all of the bad stuff. But as we will see later on, if we move to non-deterministic finite automata, then we can somehow draw a much smaller automaton that only has the good, the useful stuff in it. But anyway, sort of there is a general pattern in this mess. This kind of idea, this kind of construction that we made doesn't just work for this finite language, it works for any finite language. You just need to do a different amount of work. Beautiful. Okay, so every finite language can be accepted by a DFA. But can every language under the sky be accepted by a DFA? Wouldn't it be nice if this is true? Because we love DFAs. If they could do everything that we want, then this would be fantastic. Well, unfortunately, as your colleagues here are saying by shaking their head, the answer is no. Why? Well, I'm going to give you two reasons why. One of them is the macho reason. The other one is the less macho reason. The macho reasoning is the following. There are a hell of a lot of languages out there. Unfortunately, the number of DFAs is not big enough to recognize them all. There are many more languages than there are DFAs. Ergo, not every language can be accepted by a DFA. Now, you can believe this macho argument or not. And in fact, later on in this course, we will see some general arguments that substantiate what I've just said. Namely, the number of languages is way bigger than the number of DFAs. So we have too few DFAs actually to do the job. However, even if you believe this argument, if somebody asks you, okay, there is a macho guy there who told you that there are far too many languages and too few DFAs. But can you give me an example of a language, of a specific language that DFAs cannot accept? And by the way, make it a simple example. Then what do you do? The string of numbers.
Like if you have an irrational number. Like
Okay. So your colleague up there is talking about irrational numbers. Yeah, but let's make it. That's too complicated. It has something to do with the macho proof. So here's an example of a language that, in fact, you have already seen, and that DFAs cannot accept. This is the language that consists of all the bit strings that start with a block of zeros, followed by a block of ones of the same length as the block of zeros that preceded it. And the length of this block can be arbitrary. It can be 0, 1, 2, 3, any. Now, DFAs are not sufficiently powerful to recognize this language. Okay, that's a claim, but how can we prove that? Now, I cannot resist the temptation to show you the proof. Because actually, it's not a mind-boggling proof. Doesn't mean you will understand it straight away. All of you will understand it straight away. But the general flavor of the proof is something that you can all understand by looking at it for 5 minutes and thinking about it. So I apologize beforehand, but just I have to show it to you. It's just too cool and too nice. Okay, so what is it that I want to show? My claim is the following. No DFA under the sky can accept this language. Now, this is a strong claim. It just says, well, it says that no matter how hard you try to beat the DFA, for this language, you will never succeed. So it has nothing to do with your ability to program with DFAs. It's just something that DFAs cannot do. Even if you tell Einstein, build me a DFA that accepts this language, Einstein will fail. Why? Because there is none. There's no point in looking for it. Okay, so how can we prove this? Okay, and you will I think you will accept the fact that I'm going to try and make it as simple as possible, and I will consider some example. Okay, just the pattern of the proof is as follows. We proceed by something which is called by contradiction. Not contradiction, contradiction. So how does this work? We actually assume that we have built a DFA that accepts this language. And out of this assumption, we will generate a contradiction. Bullshit. Okay? So the conclusion will be there is no DFA, because if we have one in our hand, we assume that it does the job. It really doesn't do that job. Okay? So how do we proceed? Assume that M is a DFA and M actually accepts this language. So let's call this language A. The language accepted by M is A. Now, M is a DFA that accepts this language. It means it accepts all of the strings in this language and no other. It only accepts strings of this form and no other. Okay? Since this is a DFA, it will have some number of states. Okay? Let's assume, by example, it has 5 states. What we are going to do afterwards does not depend at all on the fact that it has 5 states. The pattern of proof will work even if it had 3 billion states, or the number of atoms in the universe states. Okay? So let's assume that M has 5 states. Well, 5 is not a magic number, it's just a specific number instead of k states for some k, just to make everything very concrete. Okay, so this automaton accepts all of the strings of this form. So in particular, M accepts the string 0 5 times, followed by 1 5 times. Since it accepts this language, in particular, it must accept this string. As soon as there's something you don't understand, scream. Okay, your colleague is saying, I still don't get it, but the answer is probably because there's nothing to get so far. So what is it that you don't get specifically? So I'm assuming that M is a DFA that accepts this language. Since M is a DFA, it has a certain number of states. I'm assuming, for the sake of concreteness, that it has 5 states. Then what I do works no matter what you put instead of 5. Okay? Since M accepts every string of this form, in particular, it will accept a string that starts with 5 zeros followed by 5 ones. Why? Because that's a specific element of this language, capital A. Okay, so now let's feed our automaton with this specific string, 5 zeros followed by 5 A's. Yes, question.
But a DFA, it can accept this specific language, right? 5 zeros and 5 ones.
Okay, just a second. The question is, a DFA can accept this specific string. Absolutely, absolutely. But this DFA does not just accept that string. That's an example of a string it accepts. It accepts every string of this form, n A's followed by n ones. We have assumed that it accepts every string of this form.
The reason it doesn't work isn't it just because the DFA would have to be endless?
Okay, your colleague is saying the reason why it doesn't work is because the DFA would have to be infinite, which is not allowed to be. That's where we are getting. But that's not a proof. The DFA will have to be endless. You have to convince me that the DFA will have to have, well, it cannot have any finite number of states. Okay, so that's where we are getting. That's where we are getting. So let's simulate this automaton, this DFA with 5 states, on this input string that it's supposed to accept. It starts in the initial state. It reads the first 0. Okay? It goes to another state. Possibly the same one, possibly not. It reads the second 0. It goes to another state. It reads the third 0. It goes to another state. It reads the fourth 0. It goes to another state. It reads the last 0. It goes to another state, from which it will read 5 ones, and it will reach a final state. That's an accept state. That's a snapshot of the computation of my automaton. It has to have a computation of this form, in fact, exactly one computation of this form because it is deterministic, because it has to accept this string. Now, let's look at this part of the computation. How many states have we gone through in this part of the computation? How many states are there? 6 states. S0, S1, S2, S3, we can count them. There are 6 of them. Can they all be different? Okay, we have 5 states in our automaton. We went through 6 states. Can they all be different? No, because we don't have 6 states. We only have 5. So somewhere in here, we have visited the same state twice at least. What does this mean? This means that in here, in this computation, there was a loop. So we've gone from S0 to some state. So let's say, for instance, that S1, just for the sake of concreteness, is the same as S4. Here we read 2 A's, no, 1, 2, 3 A's. We read an A here, an A here. Then we go to S5, from which we read 5 A's, and we go here. From 5 1s, sorry, and we go to the final state. Now, what does this tell us? This tells us that this automaton accepts, for instance, a string with not only 5 zeros followed by 5 1s, but also 8 zeros followed by 5 1s. Why? Because we can go through the loop twice. And that string is not in the language A. So we should not have accepted it. What is the conclusion? The conclusion is that every DFA that accepts all of the strings in this language will accept more, not only those. Okay, your colleague is saying, Luca, you're bullshitting us. You assume that, well, he didn't exactly say that, but that was the meaning of what he said. Well, what is wrong here is that you assume that it had 5 states. Well, let's generalize. Let's say it has k states. Then what is it that you need to do? Instead of taking this string here, you take the string k zeros followed by k ones. And then as you read the first k zeros, you will have to go through k plus 1 states. But you only had k. So you can repeat the same argument. There has to be a loop while you read the first k zeros, which means that you accept more stuff than you did, because you can go through the loop as many times as you want. Your colleague, the same one who was pointing out about the infinity of the states, he said, why do you have to assume that your DFA will have some number of states? Because your DFA only has a finite number of states. Because it is a finite automaton. If you could have infinitely many states, then no problem. You could actually accept this. But I wouldn't want you to write down an automaton with infinitely many states. You would write a lot, far too much. Okay? What is the message? The message is this language, specific language, for which you've actually generated, given grammars to generate the language, as very simple grammars, cannot be accepted by DFAs. What was the grammar for this language? The grammar was simply S goes to lambda, S goes to 0, S1. 2 productions. Grammars can do it, DFAs can't. Tough luck. Tough luck. Why tough luck? Because this may seem like a very strange language, but it's something that when you're doing LaTeX programming, you would like to recognize. The first n zeros are open curly braces. The last n ones are closed curly braces. And you want to have them balanced. A DFA cannot check that for you. So who are you going to call? Grammars. Okay, rest assured I will never ask you to repeat this proof anywhere, but I had to show it to you so that you can exercise, you can strut your skills at your next party. You know, so you go to somebody you want to really impress and you say, you know, I know some language which is not regular, that cannot be accepted by a DFA. And then there will be emptiness around you. if you want to stay quiet and enjoy your beer, that's the best way to do it. Okay, now we take a break, and after that, we continue with DFAs.